So this chapter is about the graphs. So we'll look at a couple of different types of graphs and try to see how we can use the graphs to solve some real-life problems sometime. So these are, okay, first of all, this is one type of graph which is called taper lines graph, like these ones. This, you know, as you can see, these are just like a scale, right? So here, as you can see, we start from the left side, 0, right? It doesn't matter. It may be starting from different number, because it depends on where it is explained, how it is explained, why it is needed, based on that. And also, it's not necessary that we mark every single thing in the graph. For an example, we basically try to mark what? 0, 5, 10. So let's say if somebody needs 7, you'll be able to find it here, right? Because you'll be able to find from the small ticks. Remember when, so here in general, we call these ones at major ticks, and these small ones are called minor ticks. Okay, so we can use these to just, and also this division, for an example, this long one is called major division. These small ones are called minor divisions. Okay, so we can also find how much is one minor division worth just by doing a little math. So what we can do is we can just find it by dividing the incremental values by the major divisions by the number of the blocks between the division. For an example, let's say, what is the difference here between two major division, consecutive division? The difference is, let's say, 5, right? And how many minor divisions do we have inside? We have minor. I'm not talking about the major. So 1, 2, 3, 4, 5, right? So pretty much since we have 5, the difference is 5 between the major division, and a number of minor divisions is 5. So each minor division is worth 1. In this case, it may be different in other graph, right? So that means read like this is 0, then 1, 2, 3, 4, and then 5. Again, this is 6, 7. So, this is the same one. Now, between 10 and 15, we read how? 11, because every minor division is 1. This is a minor division, so it's 11, 12, 13. That's how we read, right? Now, how do we plot a graph? There are different types of graphs. In general, we first determine the variable. There are two different, at least there will be multiple variables, right? So in general, we have two different kinds of variables. One is a variable called independent variable, one variable called dependent variable. Now it depends on the problem. Okay? We'll take a couple of examples and we'll probably have a little bit better understanding. And then we select suitable graph type and graph paper. We label the axes, because since I said we have multiple variables, we'll have multiple axes. We'll show you that as well. So, and then we assign values, and now it depends that how we assign the values. As I said, we do not have to mention every single value, so we skip the value, right? Just like the last one, we started from 0, and then the next value was 5, right? Then 10, 15, we skip 5. Now it depends. Maybe skipping like 1,000. It depends on how many data you are trying to feed in one graph. Now, let's see. So these are different types of graph. For an example, this is one graph, right? This is a different graph. Now, what is the difference here? For an example, in this graph, so along this axis, this is one axis, okay? And this is the other axis. So there are two different axes here, right? This is one axis and this is another axis. So there are two axes. And also, there are two variables. Look at this. One variable is here, time passed. This is one variable which is given in hours. Another variable is temperature, which is given in degrees. Now, between these two variables, remember I mentioned if there are two variables, one is dependent and another one is independent. Now here, time is an independent variable, but temperature is a dependent variable. Why, first of all? First of all, because we are, let's say, trying to basically measure the temperature of something over the time. You know what I'm saying? So basically, time is like an independent thing, but temperature depends on the time. That's why the temperature is dependent. And almost in all cases, we basically plot the independent variable along this line, meaning along the horizontal line, meaning horizontal axis, which is also called x-axis. Okay? And dependent variable is plotted along the vertical line, which is this one, right? And a lot of times this is called y-axis. And as you can see the values here, so here you see the values are 1, 2, 3, 4, because you know these are in hours, right? So you probably don't need more than 7 hours for an example. But here we cannot go by just 1, 2, 3 because degrees may be like more than 1 degree, right? So for an example, we know that our data may not be more than 40 degrees, so that's why, or 50 degrees. So we just started from 10, right? But as you can also see, there are skips here, right? So each minor ones, can you tell how many is what this is minor one? Let's say this is 0, right? This is 10. Now between 0 and 10, how many minor divisions you have? 1, 2, 3, 4, 5, right? So for 10, there are 5 divisions. So you watch one division, what? 2, right? So let's say if I have to plot 22 degrees, it will be here, right? 22. Okay. Now this is a different type of graph. We want to show you that the graphs may be absolutely different. Now here in this graph, we have some types of lumber, and we are trying to plot the cost of those lumbers, average cost. Okay. So types of lumbers are like independent, but cost of lumbers are depending on what type of lumber we're talking about. So there are 3 kinds we have: pine, oak, and cherry. Now remember, these are the cost. Now the costs are basically given as dollars per 1,000. Okay, 1,000 board feet, meaning let's say this is like $10. The price is for 1,000 feet. Okay, $20 for 1,000 feet. Now, if you look at this graph carefully and this graph carefully, look at this. Here, we plotted the time in sequential order, right? Like 1 hour, 2 hours, then 3 hours, then 4 hours. So they have a sequence, and you cannot basically swap the sequence. Pretty much like you cannot put like 4 first and 3 later, because those are hours, right? And those have some incrementing property, right? Because it's time. But here, it doesn't matter how we write those numbers. We started with pine, right? But we could have started with cherry, right? If I start with cherry here and then pine later, doesn't matter. So it depends on what exactly you have in the graph and what do you need, okay? So these are different types of graphs I'm trying to show. And this is another type of graph called line graph. There are plenty of types, but most of the time people use their graphs based on what exactly they need to show to the people, okay? To the let's say or or present to the audience. It depends. So, but always the idea is you want to show a plenty of information in one single drawing, because let's say this graph is showing you the average percentage of quiz score for a class, let's say for this class. Okay. Now, if you look at these, let's say they have 14 quizzes. I'm sure they have plenty of students and 14 quizzes, and they try to take the average, and the average shows that at the beginning there are 70%, and then later falls, and then again it rises, right? At some point and at the end it was like 100% close to. So the most of the people did really well at the end, but there were like ups and downs, right? But just by looking at this graph, you can see exactly how the class performed compared to if I just give you a big sheet of all those numbers of the every student, and you have to read and you have to think and see and then find out exactly how the class performs. The graph. So a lot of times the graph shows the whole thing in a very nice way, very quick. Okay, so that's the idea. And again, that's why people try to choose different types of graph based on their problem. As I said, it depends on the problem. So this is again another way of representing the same one. Okay. But the reason we put some scales like these, or in the previous one, a line like this, we just want to show that how the data graph are rising or falling. It's rising inward. Most of the students in class are doing better. Okay, most of the time. Another graph. This is called bar graph. So pretty much all the data are given as a bar. So here, these are different age of the storage tank, and these are frequency of the tanks, meaning the number of tanks. Now let's say you are trying to show that in one area you probably do the survey of all the storage tanks, because some storage tanks are less than 5 years old, some are like 20 years old, right? And how many are those different tanks there for different age groups? So you just do the plotting, and just from the plotting, let's say somebody tell me, okay, how many storage tanks you have with the age 10 years? Because all the age are given 80 years. So how many? So for 10 years, we go here, right? And this is the age, this is the number of tanks. So pretty much you have 30 tanks with age 10, right? But look at this difference. For this graph, if somebody wants to say, okay, can you tell me what is the number of tanks you have for age 7? We don't have it here. There is no 7 there, right? We can find the 7, but I'm just trying to show the difference. Look at this. The 7 asking that question for this graph is like, doesn't make any sense. We don't have any 7 here. We don't have any 12 here, right? Because these are some specific intervals between the data given, right? Again, another graph. I'm using this sort of graph a lot. In most of the cases in like advertisement and in different explanation of different things. So this is called a circle graphs. This basically shows you, let's say for an example here, we are trying to show the cost of a business. And that basically gives you an idea that where the most of the budget is going. For example, the 30%, which is largest out of these, which is basically the greatest chunk of the circle, is in the payroll, right? And the lowest is what? The profit, only 5%. So, just from this one, you can guess that how the business is running, where the most of the money is going. Another sort of, another, that's the same thing, but we just try to show you the data here and then draw the pie chart or circle graph. This is again another example, but let's see whether we can answer some question from here. So here we have a 6-month period starting from January to June. And here, let's say this is a car dealer, and they are trying to compare their projection and actual thing. A lot of times they try to, target something that, okay, we will sell this many vehicles this month, but they may not be able to sell that many, but they might sell less or more, right? I'm saying more is good always for them. So here, if you look at this one, all the gray ones, gray bars are like the projected ones, and the black ones are the real sale. So for an example, in January, they are projected, can you see January the projected was 26, it's 25, right? So between 25 and 30 there are 5 minor ticks. So each one is 1. It's 26. So their projected was 26, but actually they were able to sell 21, right? Same is February. I'm saying not same. I'm saying the February they have more sales than projection. Their projection was 11, but they were able to sell 15, right? So can we answer this question from this graph? What is the total number of cars projected to be sold during entire 6 months? How do I know it? What we can do is we can add all the projection, right? So for an example, this one is 26 and this one is 11. This one is 18, right? How about this one? 22, 25, and 30, right? If you add all of these, that's your total projection, right? Now, how many how many vehicles are sold? You can just add all the black bars, right? Black ones are the actual ones. So here 21, 15, 16, 25, 30, 30. Then you get the total sales, actual sales. So what is the average of the entire 6-month period? All you need to do is you have to divide this total by 6, right? This is the actual sales. That's the average. Another example, let's say somebody gave us this circle graph, and these circle graphs represent the causes of death of people aging 15 to 25. Out of 1,000 fatalities, they try to use, let's say, in Saudi and see how much. So out of, let's say, 1,000 people, 15% died for drugs, 10% disease, and 35% auto accidents. And we have another 2 categories. One is suicide here, but the percentage is not given. Another one is accident, but the percentage is not given. So that means we have to find out. Now, how many people died from automobile accident? Here. How do I find it? See, it's 35%, right? And the total fatalities was what? 1,000, right? So remember, in the last chapter we are talking about the percentage, right? So this is the time you can apply it. So you have what? You have the rate, 35%, right? And you are also given the base, which is 1,000. So pretty much you are trying to find the portion. What is the formula? Base times rate, right? So remember, the rate is given as fraction, right? 35% means 0.35 because you just moved the decimal point 2 positions to the left. So it's 1,000 times 0.35, which means 350. That means the people died out of auto accident is 300, right? Any question here? Let's try another question. What is the percentage of fatalities caused by suicide? Remember, the people died out of suicide is 100. It's given, right? But we don't know the percentage. So that means what? For this case, we are given, we have to find the rate. We are given the base, we are given the portion, right? Base is what? 1,000. Portion is 100. How do I find the rate? Rate is just P by B, right? Portion is 100. Base is 1,000, so it's 0.1, which means 10%. See, we are using that, applying the formula from the last chapter, right? So, that's how our things work. We learn something and apply it to the next topic. What is the percentage of fatalities by non-auto accidents? Now, this is the time. Let's look at the graph here. See, this is 35%, this is 15%, this is 10%, and this is also 10%, right? We just found this is 10%. So if you calculate all these percentages, how much you get? 10 plus 15 is 25, plus 35 is 60, plus 10%, 70. So you are left with another 30% because the total graph should complete 100%, right? Now you know the accident but non-auto accident fatally reserved 30%. That's how we can use a graph, and we can find, we can solve some problems and find a lot of other information just using the graph. Okay, this is a small chapter, so we have quizzes also in the quiz section, but we'll first do the test. Okay, so we'll stop the presentation here for today.